everybody, so this is the Semester 2 final exam review problem. This is going to be the explanation and solution of problem number 1, which reads, a roller coaster car of mass 2,150 kilograms is moving at 8 meters per second at the top of a 33-meter tall hill on a frictionless track as shown below. So we're going to start by solving for part A, which is what is the gravitational potential energy at the beginning, and we know the gravitational potential energy is the same as Eg, or Eg equals mgh. So knowing that Eg is equal to the mass of the car, which we were told is 2,150 kilograms, times g, which is the gravitational constant, or 9.8 newtons per kilogram, times the height of the car at the beginning, which is 33 meters, we can easily solve for the gravitational potential energy by plugging that into our calculator. So 2,150 kilograms times 9.8 times 33 gives us 695,310 joules of energy on the calculator. There. So we can say that Eg is equal to 695,310 joules. And that is our answer to part A. So now moving on to part B, we are asked to solve for the kinetic energy at the beginning, and we were told that the cart is originally moving at 8 meters per second. And so knowing that Ek, or kinetic energy, is equal to 1/2 of the mass times the velocity, we can also solve for Ek. Ek being 1/2 of the 2,150 kilograms, as stated before, times the initial velocity of the cart, which is 8 meters per second, squared. And again, this is a job for our calculator, so we have 1/2 times the mass of the car times 8 squared, which is actually 64, gives us 68,800 joules. So we know that Ek is equal to 68,800 joules. And that is our answer to part B, the initial kinetic energy of the cart. Part C then asks us, at what point will the car have the greatest potential velocity, or the greatest velocity? And for that, we need to look at the image presented on the worksheet. And so here we have point A, I guess, where the car starts, point B at the bottom of the ramp, point C at the top of the loop, and point D after the cart has slanted back upwards somewhat. And so we know that the greatest velocity is going to be where the cart has the greatest kinetic energy, and we also know that energy is conserved. And so because the cart, we're looking for the point where the cart has the least gravitational potential energy, since the least potential energy will maximize the greatest kinetic energy. And so we're looking for the height of the car, since potential energy depends on the height. And so we're looking for the lowest point of the cart on the track, which is going to be at point B. This means that at point B, the cart is going to have the greatest velocity, which is what part C asks for. So we can say point B. Now part D asks for the velocity of the car at point D, which is here after the cart has gone back upward somewhat. And so what we can do here is we know that since energy is conserved, we can set the initial energy and the final energy equal to each other, aka Eki, which we solved for up here, to be 68,800 joules, plus Egi, which we solved for again earlier, for 695,310 joules, is going to be equal to our ending energy, which means Ek final, so Ekf plus Egf. Now we can solve for Egf, since we do know the mass of the car, the gravitational constant, and the ending height of the car, which is 7 meters here. So solving for the final gravitational energy, we have Egf is equal to the mass, which is 2,150 kilograms, times 9.8 newtons per kilogram, times the height, which is 7 meters. Again, plugging this into our calculator, we end up with 147,490 joules. Now, since we're solving for the velocity of the car, and velocity is dependent on the final kinetic energy based on this equation, we can solve for EKF by plugging our new energy, our final potential energy, into this equation. And so we can say that 68,800 joules plus 695,300 joules is equal to 147,490 joules plus EKF. And I hope it's clear where all those numbers came from. We have our initial kinetic and potential energies, and then our final potential energy here. So then solving for this equation, we can say that EKF is equal to 616,620 joules. So now that we have EKF, we can plug that into our normal EK equation, since we do have the mass of the car isn't changing, and we can solve for the final velocity of the car. So we have 616,620 joules is equal to 1/2 2,150 kilograms times velocity squared. Now, once again, plugging this into our calculator, we can say that the ending velocity, the final velocity, is equal to 23.95 meters per second. You can see that in the calculator here. And so that will be our answer to part D. Now part E is how would you change your answer to part D if you doubled the mass of the car? And so what we have to do here is we have to take every place where we would have put in a mass and we put in 2m, or 2 times 2,150, right here, 2,150 kilograms. And so what we end up doing is we have EG, I, is now equal to 2m times, we'll call this 2 times 2,150 kilograms times 9.8 times the height originally, which is 33 meters. And we'll just make this easy, and we'll say that 2 times 2,150 is 4,300 kilograms, and we'll use that for all the rest of our equations. So, so 4,300 kilograms times 9.8 times 33 meters gives us a very large number. It gives us 1,390,620 joules. And that is our initial potential energy, And we do the same thing to solve for the kinetic energy, which I will now do on the next page. Okay, so we have EK here, and EK is equal to 1/2 times the mass, which we established is 4,300 kilograms, times the velocity squared, which we know is 64 meters per second. Well, technically meters squared, second squared. But so solving that, we have another very large number, although not quite as large. We have EK is equal to 137,600 joules. Finally, we recalculate EK final. Oh, this is EK initial. And we recalculate EK final, EG final, or the gravitational potential energy final. And we have that equals 4,300 kilograms, which is the mass, times 9.8 newtons per kilogram, times the height, which is 7 meters. So we have 4,300 times 9.8 times 7, and that gives us that EGF, is equal to 294,980 joules. So now we can set that up in our original equation, or well, not our original, but in our equation once more, saying that EKI plus EGI is equal to EKG, or EKF plus EGF. And so we have, from here, we have 1,390,620 joules. So 1,390,620 joules plus 137,600 joules is equal to EK final plus 294,980 joules. Now these numbers might be easier to store in your calculator. I haven't been doing that, but it may have been a smart idea to do so. So we can type in these numbers again and solve for our final kinetic energy. And so we have that our final energy is equal to 1,233,240 joules. Now we set that equal to 1/2 the mass, which is now 4,300. Oh, that should there should be kilograms here. Kilograms times the velocity squared. So we're resolving for velocity now. We have 1,233,240 joules divided by 0.5, and then that answer divided by 4,300 joules. Take the square root, and we end up with the same answer. The velocity equals 23.95 meters per second. And so our answer here is that velocity does not change. Now this may have actually been easier to see if we had set up our equation in terms of variables initially. And so let's do that right now. We know that EG is equal to mgh, and we know that EK is equal to 1/2 mv squared. So if we set up our EK, EG, final and initial and final from before, then we can say that mgh plus 1/2 mv squared is equal to mgh plus 1/2 mv squared. Now we can see that there's a mass in every single one of these equations, and that means that we could potentially factor out mass, or in this case, because mass remains constant, it doesn't affect any of the other variables in the equation, which includes velocity. So here you have the answers to problem 1 of the semester 2 final exam review problems. You can also check those answers in the back of the packet here, in which case we have 695,310 joules, 68,800 joules, point B, 23.95 meters per second, and that the mass would not change the velocity as we have established. There you go.